Okay, good afternoon. First of all, apologies. I didn't manage to get the lecture video done for Wednesday. So now my plan to get caught up on is I already have my annotations on there. And so what I'll do is instead of doing live annotations, my annotations on there, but we'll be doing live class, meaning I'll go over everything and explain everything. But in the interest of saving time and getting caught up, my writing and everything is already there in the class notebook. Okay, so we'll cover a big chunk today, and then about 10-15% on Monday, and then by Wednesday we should be all caught up, back in line. Okay, that's the plan. All right, so let's see. I'm going to do large signal models. All right, so in the BJT, we looked at operating mode and determination of operating mode based on the terminal voltages, right? So there are two kinds of analyses or models we can use. There's large signal and there's small signal. And each one of them has their specific applications, right? So let's take these large signal models first. Large signal models, we are looking at the three modes of operation, which is cutoff, saturation, and active, right? And we know that when both junctions of the BJT are reverse bias, the transistor is in cutoff mode. Well, cutoff mode is so called because there's no output. The only amount of current that's flowing through is basically a very small saturation current. There is no voltage drop across the base and the emitter, and IB is equal to 0. So we can model the base or the base terminal as an open circuit, right? Open circuit. So no current is actually flowing into the junction. Again, base emitter is reverse bias. So it's reverse bias. There's no charge carriers being generated. The only carriers that are flowing through are the minority carriers, right? And so we can represent the base as an open circuit, and there's a very small current that flows between the collector and the emitter, and that is known as ICEO. And this is similar to the reverse saturation current, so very, very small. Okay, technically this means the collector emitter current when the base is open, ICEO. All right, so that's in the cutoff mode. In the saturation mode, both junctions are forward bias, and because both junctions are forward bias, VBE is equal to the forward diode voltage drop. In this book, the author refers to that as V gamma, which is over here, right? That's the forward voltage drop that's required for the emitter junction and the base junction to be forward bias and turned on. And then, since the collector base junction is also forward bias, VCE drops to a voltage level of 0.2 volts or less, which is known as saturation voltage, or VCE SAT. And VCE SAT, as we mentioned earlier, is approximately 0.2 volts or less. Okay, so in this saturation mode, the voltage at the collector and emitter and the base and emitter is pretty fixed. And so we can represent that both of those as constant voltage sources, right? Because the voltage is not going to change, there is a constant voltage source. So we can model both junctions as voltage sources. So here's V gamma, that's the voltage that's required to turn on the base emitter junction, and then VSAT is the VCE. Okay. And then finally, one of the most important mode, well, depending on our application, is the active mode. In active mode, VBE is still forward bias, but the collector base junction is reverse bias, right? So VBE, V gamma, is the same as what we had for saturation mode, which is about 0.6 to 0.7. Here it'd be about 0.6 to 0.7. And then on the collector side, because it's the active region, the output collector current, which is flowing in this direction, is equal to beta times IB. Remember, in saturation, the current does not change, remains at a fixed level. Here, it depends on the value of the base current. In saturation model, the base current could vary, but the output current is saturated, so it would not change. So the current gain, or this expression, is not true in saturation. Okay, this is not true in saturation because current is already saturated to a max level, and it's like a horizontal line, right? So this is or this behavior can be described as a dependent current source. It provides an output current, which is the collector current IC, but IC is proportional to IB. Hence, it is a dependent current source. Independent current source, again, is very useful for modeling. And one of the most important models of a BJT transistor, which we teach in 306, not in this class, is based on this dependent current source model on the output side. So the output is dependent on the input current. Okay, so these are the three models in brief. Okay, now we said that depending on the biasing voltages that is applied, the mode of operation can change, right? So when we first begin and we apply DC voltage, we are trying to design a circuit with a BJT, we're applying DC voltages. Well, the application of DC voltage means we are biasing our circuit, we are biasing our device. Okay, so biasing in this case is the application of DC voltage. And by choosing the appropriate choice of IB/RB, actually, wait, this is wrong in there. Hold on. Yeah, that's the wrong slide. Amplification, C amplifier, 829. Pause. About that. Okay, so now KVL at the output. If you apply KVL on the output side, you have VCC, you have the voltage drop across RC, and you have VCE, 3 voltages. So we can write VCC is equal to ICRC plus VCE. And then VCE is equal to VCC minus ICRC. And therefore, collector current IC can be written as VCC minus VCE over RC. Keep this equation in mind. This is the reason, or this explains how and why the output of an amplifier is inverted. So just jumping ahead a little bit. If IC increases, the voltage drop across RC increases. If that voltage drop across RC increases, then VCE decreases. So VCE is inversely proportional to IC. IC depends on IB. It's directly proportional. So if you remember the lab, when we performed the amplifier circuit experiment, the output was inverted by 180 degrees. And this equation explains how and why that is. So IB and VBE are proportional. As VB increases, IB increases. If IB increases, then IC increases. As IC increases, then VCE decreases. So at the maximum point, you obtain the minimum value of VCE. And we will see that shortly in a few slides. Okay, so this is the equation that relates VCE and IC. To find the points of the load lines, we plug in IC and VC is equal to 0. And we can determine the coordinates for both collector current and VCE. Again, this is the load line procedure. That's the standard procedure. Nothing's changed with that regard. Only the device has changed. Okay. Only the device has changed. So now let's see. Let's see how both AC and DC work together. So if you have a BJT amplifier and we are connecting a DC, VBB, VCC, right? DC is used to set up the bias and the Q points, meaning the operating point of the transistor. And AC is basically the small signal that we apply at the input that we want to amplify or that we wish to amplify. Okay. Now, typically, I would say DC is all uppercase notations. So it's VDC, or let's see, VCE, or VCE, IC, IB, everything is uppercase, including the subscript. If it's AC, it's all lowercase. So this is going to be lowercase v, C, E, and this is going to be IC. Okay, the quantity V and I are lowercase, and the subscripts C, E, and C are also lowercase. So when it's AC, it's lowercase. If it's DC, it's uppercase. And if it's both DC plus AC, then the quantity is lowercase, and then subscripts are uppercase. Okay, subscripts are uppercase. This is standard procedure. In our book, for explanation purposes, what the author is using is delta, just to describe it as a change in the voltage and a change in the current. Okay, I just want to clarify that if you read another book, or if you're reading something written by somebody else, perhaps online, different textbook, different classroom, this is the standard. If it's all uppercase, it refers to DC. If it's all lowercase, it refers to AC. But your job as an engineer would be recognized if somebody's using the wrong notations. All right, so if you look at this on the input side, okay, this is the input side. Everything's still the same. You have the supply voltage VBB, you have the resistor RB, and you have the voltage drop VBE. So if you apply KVL, you would have these voltages and these resistors, right? Sorry, not that one, this one. But now we are also applying or sending an AC input, right? That's a signal that we wish to amplify. So on the input side, the total voltage being applied is VBB plus delta VBB. And this is going to be this is the DC portion, this is the AC portion. Okay, the delta is basically just the author's way of noting that the signal is varying between a certain range. So you have the DC VBB plus the AC delta VBB. IB again has the same component, IB plus delta IB. On the output side, we have VCE plus delta VCE and IC plus delta IC. Again, all four quantities have DC components as well as AC components. So if we wish to operate this in active mode, we bias it in the middle of the operating region, the active region. And that would mean that the collector current IC would be a function of IB. So IC is beta times IB. So IC plus delta IC, meaning the AC and DC components, would be amplified by a factor of beta, both DC and AC. Then we apply KVL at the input and KVL at the output. Apply KVL at the input, we obtain the exact same expression that we obtained in the previous slide, except every single component now has a AC component to it. So you have VBB, DC plus AC. You have IB, DC plus AC. And you have VBE, again, DC plus AC. You rearrange the terms, and you obtain this expression. Again, the expression is still the same. VBB is IBRB plus VBE. But everything else has a AC component. So the Q point is a result of the applied DC voltages, right? Meaning there is no AC signal being applied. So if no AC signal is being applied, the only thing at the input and the only thing at the output would be DC voltages and DC currents. So at the Q point, all the deltas are equal to 0. Or the delta values are equal to 0. So you would obtain VBB is IBRB plus VBE. And that means if we take that out, we can write delta VBB is delta IBRB plus delta VBE. Any change in the input voltage is going to result in a change in the input current and in the base emitter voltage VBE. Again, the equation is still the same. On the input side, we applied KVL. You obtained our supply voltage VBB is equal to IBRB plus VBE. But every component now has a AC component to it. Every quantity has an AC component to it. And that is delta VBB is equal to delta IBRB plus delta VBE. And we can write an expression for the input current, for the AC input current, in terms of the AC input voltage. Exact same form for both DC as well as AC. Okay. This exact same form is there for DC as well as AC. On the output side, same equation. VCC is divided across ICRC and VCE. You add the AC component in there, and you would obtain VCE plus delta VCE and IC plus delta IC. Okay. VCC is the voltage on the output side. It does not have a AC component to it. That is the biasing voltage. Again, on the input side, we have the DC biasing voltage VBB, and we apply an AC VBB. Hence, we have delta VBB. On the output side, we only have the DC VCC, which results in a DC VCE, and it also results in a delta or AC component of VCE. Okay, which is right here. Of course, we want to obtain an expression for VCE and IC. So at the Q point, if we don't count any of the AC components, we obtain VCE is equal to VCC minus beta IB times RC. Beta IB replaces IC. And then we realize from here, delta VCE is directly proportional to IB, right? IC is proportional to IB. And so VCE is proportional to IB. Actually, it's inversely proportional, sorry, not, it's inversely proportional. Let me make that change. Right, as IB increases, IC increases, and as IC increases, VCE is going to decrease. That's why it's 180 degrees out of phase. All right, so now we will take this expression for delta IB and plug it in here. We have this for delta IB. You plug it in here, you rearrange the terms, and you obtain delta VCE is equal to beta times RC over RB, and the input voltage VBB minus delta VBE. And that is the output voltage and the dependency on the input side. Okay. All right, let's take a pause. Think over that. Let me know if you have any questions. Any questions? Okay. One drawback of this is that the output is heavily dependent on the value of beta. If you remember the data sheets or the spec sheets you pulled up for the lab, the transistors that you use in the lab, the variation in beta was from 35 to like 200. Okay, there's a wide variation, even for the exact same transistor manufactured at the exact same time in the exact same facility right next to each other. Okay, so there's a large variation in beta. So if you have two transistors in your lab kit, for example, one transistor might have a value of beta for 35, the other one might be 200. Well, if it's 35 and 200, your design may not work, right? This is a very simplistic design with the bare minimum of components. We only have two resistors on either side to bias or control our current, right? So there are lots of quantities in there that we have to account for. So any variation in beta is going to result in a very large amplification. And instead of operating in the active region, your transistor would be operating either in cutoff or in saturation. And you'd have a distorted output. Okay, you'd have a distorted output. And we actually saw that in the lab when we diminished or reduced the input signal going to the amplifier by a factor of 10. Remember, we used a voltage divider network. We sent the input signal in there, and the output signal was very large, especially when we used a bypass capacitor, right? The output signal was very large. And if it gets too large, then it's going to drive the transistor into saturation or cutoff, which would mean distortion in our speakers. Okay. Let's move on to an example. All right, so we have a CE amplifier, common emitter amplifier. We have one resistor RC and RB on both input and output side. We are given the input characteristic. We are given the output characteristic. If you wish to perform a load line analysis on this, we are going to apply VCC and VBB. We're going to apply KVL on the input side and on the output side. Okay. If we observe the output characteristic, we can extract the information for beta from here, right? This is a rather straightforward example. If IB is 10 microamps, IC is 1000 microamps. So a factor of 100. Right? IC over IB gives us the value of beta. If you take any value here, we get 2 milliamps or 20 microamps, 5 milliamps, or 50 microamps. So beta of 100. Obviously, real-life transistors are not going to have these kind of idealized curves. Okay, so on the input side, we have, when we apply KVL, we have VBB, we have the AC voltage V in, we have RB, and we have the voltage drop VBE. So we have the AC signal V in of T, DC voltage drop across the resistor RB, VBE, and minus VBB. We rearrange the terms, and we obtained V in plus VBB as equal to IBRB plus VBE. VBB is known, RB is known, V in of T is known. The only unknowns are IB and VBE. This equation we used to describe load line. To determine the coordinates, we plug in VB is equal to 0 and IB is equal to 0, and we would obtain VBE values and IB values. When we join them, we obtain the load line for the input side. On the output side, the same thing, we apply KVL and we obtain an expression for VCE. So that is given by VCC minus ICRC. VCE is equal to VCC minus ICRC. So if IC is equal to 0, then VC is equal to VCC. And if VC is equal to 0, then IC is VCC over RC. On the input side, if there is no AC signal applied, we have this load line, right? You know, that load line. So the Q point is fixed due to the DC. Then if we apply a small AC signal on top of our DC input, which is our V in of T, then our load line is going to shift up and down based on the input signal. Because as V in increases, our load line is going to move up. So it's going to go up here, it's going to go up here. As it goes down, the load line is going to move down. For every point of V in, depends on how many points you want to take, but every point or every value of V in, we can have a different load line that either moves up or moves down. Okay. The intersection point, obviously, is the Q point on the input side. Okay. This intersection point is the Q point, which would be the same thing on the output side also. Okay, that intersection is the Q point. And again, as V in increases or decreases, then the Q point either shifts up or down the load line. The intersection point of the load line with the diode characteristic is basically the Q point. And so that can keep changing on application of AC input signal. So as an example, with the previous circuit, if we applied a VCC of 10 volts, VBB of 1.6, RB and RC are given as 40K and 2K. And then V in of T is given to us as 0.4 volts peak and 1 kilohertz frequency. Frequency, we don't really care about frequency. What we care about is the input voltage. If it says it's 0.4 volts peak, that means the signal is mathematically described as 0.4 sine of 2000 pi t. Again, omega is 2 pi f. So sine omega t, 1K gives us 2000 pi. So we need to determine the VCE values on the output side. VCE is our output signal, right? In order to determine the values for VCE, we need to know the values of IB. IB is our input current, right? So on the input side, if we apply KVL, we obtain 3 different load lines. All right, we obtain 3 different load lines. Here's the one without any AC signal, meaning at the point of transition between positive and negative. So this is VBB plus V in over RB. Again, VBB and VCC values are known to us. It's given 1.6 volts. So again, IB is VBB plus V in over RB. If V in is 0, meaning AC signal has a value of 0 or is not applied, then it's simply VBB over RB. And so we get 1.6 over 40,000, which is 40 microamps. At the same point, the corresponding value for VBB is going to be 1.6 volts. So we have the DC load line, which is 1.6 volts right here, and 40 microamps up there. So let me point that out. This point is a result of no AC or 0 volts AC, which is the same as this point. That's our original load line. And the intersection point is the Q point. That's the original Q point. Okay, that is the original Q point. Now, when you apply an AC signal on top of the DC, what do we get? We obtain, this is the positive half cycle. So when you apply AC signal, we obtain IB value as 50 microamps and a VB value of 2 volts. And that load line has shifted upwards. And so we have this 2 volts and 50 microamps. And so now our Q point has shifted up. And that intersection is approximately IB is equal to 35 microamps. Okay. What? Okay. In the negative half cycle, it becomes 1.6 minus 0.4. And so we obtain 30 microamps and 1.2 volts. So 30 microamps and 1.2 volts, which is right here and right here. We join those two lines and we see that our Q point has now shifted down. And the intersection point gives us a IB value of 15 microamps. So our input current IB is varying between 15 microamps and 35 microamps. Again, to recap, without any AC applied, if you just have your DC biasing voltage, then your Q point is at 25. When you apply the AC voltage, the AC is applied on top of the DC. So it adds up or it subtracts. Positive half cycle, it adds up. So your Q point shifts upwards. Your load line is shifting upwards. Negative half cycle, it's subtracting. So your Q point is shifted downwards. Right? That is the maximum value and that is the minimum value based on the peaks of 0.4 and minus 0.4. And so you obtain 3 Q points. These 3 intersection points are the 3 Q points on the input side. We take those 3 points because that's the value of the input current and we map them to the output. And this is what happens at the output. On the, see, IB varies from 15 to 35. So IC is going to vary from 1.5 to 3.5 because we want to find on the output side, we'll find the line that corresponds to IB values from the input. So 15, 25, and 35. Okay. If you apply KVL at the output, we have our standard expression. VCE is equal to VCC minus ICRC. Plot the load line. We just need to plot one load line. If IC is equal to 0, we get VC is equal to VCC, which is 10 volts. And right here. And then if VC is equal to 0, then IC is VCC divided by RC. And that is this point up there. When we join those 2 points, we obtain our load line on the output side. Now, once we have our load line, we can see it intersects all of these points, all of these data lines, right? IB on the output side, we have the function, we have the plot values of IC as a function of VCE. But each data set is for one value of the input current IB. So this is 5 microamps, 10, 15, 20, all the way to 5050. We are only interested in 3 points. The Q point, which is 0, minimum, and maximum, which correspond to 15, 25, and 35. So we find the line for those 3, which is here, here, and here. This is the line for original Q point. This is the max, and this is the min. And the intersection point of the load line with these output curves is the solution for IC and VCE. Okay, for IC and VCE. And so the values that we obtain are here. And then, of course, IC is 3.5, 2.5, and 1.5 milliamps. We have a couple of minutes left. I want to draw this diagram. Let's say, let's make this perpendicular. Let's say you're applying an IB signal that looks like this. Okay, it's not to scale, but that's the idea, right? Okay. IB varies between 15 and 35 microamps, very small. What is the value for IC? My output value for IC is varying between 3.5 to 1.5 milliamps, gain of 100. So when IB goes max, this is IB max. Right? This is the max value of IB. You get a corresponding value for IC that is at its maximum. But at the same point, what do we see? We see that VCE is at its minimum value. Again, remember, this coordinate is the one that gives us the solution for IC and VCE. So when IB is maximum, IC is correspondingly maximum, which makes sense because IC is beta times IB. But then you see VCE value that it's at a minimum of 3 volts. And then at 0, VCE value is 5 volts. So somewhere over here, let me plot this out. And then when IB goes minimum, which is, let's point this out like this. Then IC is also minimum. But VCE goes to its maximum value. And so you obtain a VCE value that is 180 degrees out of phase with the input. Or as we say, it is inverted. So again, input side, minimum value of the input gives us, minimum value of IB at the input side gives us minimum value of IC at the output, but it gives us maximum value of the output voltage, VCE. And hence, there is an inversion of the input to the output. Plus, there is a DC component added on. If you look at this plot, your VCE, and this is, of course, sideways, your 0 is here, This is 0 volts. And this is 5 volts. So if I was to plot this, it would look something like this, the voltage. That's too small. It's the input. This is 0. And this is 0 volts. 5 volts. And it's like the frequency would not change, of course. So this diagram is not scalar accurate. The frequency does not change. But the voltage is inverted. It's 180 degrees out of phase. It's amplified. Plus, it has a DC component. So the output of an amplifier will have a DC component, plus it will have 180 degrees phase shift. Okay. All right, let's end class here today, and we'll pick up here again on Monday. There'll be a homework that I'll post later on, and quiz on Monday will be based on fundamentals of BJTs and a little bit of load line analysis for BJTs. Okay. So if you have any questions, reach out to me. Today I'll have a few hours before evening, and then tomorrow and Sunday I should pretty much be available. Okay. All right. Have a good weekend. I will see you all on Monday.